This is our next example in which we have basic electrical circuit, that is an RL circuit here. Here we want to determine the state equation of this system. First of all, we want to write the loop or node equation. We can take help from KCL and KVL. Okay, if I want to write a KCL equation here or KVL equation here, I can write a loop equation or KVL equation. This will be equals to E of T. Input voltage is equals to voltage across resistor plus voltage across this inductor. Okay, this is my equation. Now I want to represent the state variable here. Here we have only one energy storing element, that is inductor, and inductor stores energy by virtue of current. So if I want to define state variable, my only state variable x1 is the inductor current I of L. This is a series circuit and we have only one current here, which is equals to IL. So I want to find x1 dash, which is equals to dIL. So how this current will change? This can be evaluated from this equation. This is VL, and we know the mathematical model of inductor is equals to VL is equals to LdIL. So how we can write it here? Using Equiscope, we can name it this equation number 1. So using equation number 1, I can write, and second state variable will be the input, which is E of T is my state variable U. So I can write E of T is equals to VR can be written in terms of I L into R plus L D I L. IL is basically a state variable. E of T can be replaced with the state variable U. IL is basically x1R plus LD x1. This is x1 dash, so x1 dash can be written as minus R over L x1 minus plus U over L. This is my only state equation here. This is a single energy storage element and we have only one state variable here, and whose state equation is this. So this is my state representation of this basic electrical circuit. This is very simple example because this is a series circuit and we have only one energy storage element here. So we can move toward the next example, which is basically a series RLC circuit. Let's see this. Obtain the state equation of this circuit. This is a basically series RLC circuit, and we know that we can write the equations of this loop equation here. So loop equation will be E of using Kirchhoff voltage law, I can write E of T is equals to VR plus VL plus VC. This is my equation number 1. Here we have two energy storing elements. One is this inductor, second is the capacitor. Inductor stores energy by virtue of current. Similarly, capacitor stores energy by virtue of voltage. So we will have two state variables here. So state variable will be x1 is equals to inductor current and x2 is basically my capacitor voltage Vc. These are the two state variable. Third state variable is basically your input E of t, which is replaced by U. From this figure, from this question, we can see that this is a series RLC circuit. Here the current through this inductor and the capacitor will remain same, so I can write that here I is equals to IL is equals to IC. So these are the two state variables here, I is equals to, and we want to evaluate x1 dash and x2 dash. X1 dash means x derivative of IL and derivative of Vc. From this equation we can find x1 dash. How? Let's see. This is my input using equation 1. E of t is my input. This VR can be written in terms of I into R. This is series circuit. IL is equals to IC is equals to I through this R. So I into R plus VL is equals to L D IL plus VC is equals to VC. This is my equation number 1, which now I can transform this equation with the state variables. E of t can be replaced with the help of U. I is basically the IL, IE and IC are equal, so I can replace it. This is x1 R. This is basically LDIL, x2 dash, L, IL is x1, and this will become x1 dash, VC is x2. So my equation x1 dash, I can evaluate x1 dash easily by rearranging this equation. This will become minus R by L x1 minus 1 by L x2 and plus U over L. Okay, this is my equation A, static equation, first static equation. Now I want to evaluate x2 dash. X2 dash will be dVc. Okay, I want to evaluate now x2 dash is equals to, this is dVc. Basically I know that mathematical model of capacitor is equals to IC is equals to C dVc. Here in this question we have a series circuit. IC is equals to I or IL, so I can write IL as IC is equals to IL. Series circuit where current remains same, so this will become C dVc, and this term will become C IL equals to C dVc. IL is basically x1, this is C, this is my x2 dash, so our x2 dash is equals to 1 by C x1. This is my second state equation. So these are the two state equation which is representing this whole system. So I can write the state space model here. My x1 dash, x2 dash is equals to, x1 dash is equals to minus R by L x1 minus 1 by L x2 plus U over L. So it will be minus R over L minus 1 over L x2. Similarly for x2 dash, we have dependency on x1 1 by C, no dependency on x2, so this is is x1, this is x2 plus this is my x1 dash, it depends on u as well. This is 1 over L and this is not. So this is the state space representation. If I say my capacitor voltage is output, then I will substitute, I can write my voltage of capacitor is x2, so I will write 0, 1. If Vc is output. So this is basically the state space representation of this electrical system. I hope that this thing is clear to you. This is an easy questions. If you have any queries, then you can ask in the live session. Okay, this is third example of an electrical system in which you want to obtain the state equations of the system here, and here I2 is considered the output of the system. I2 is basically the current through this inductor number 2. First of all, we have to write the loop and the node equation. So I will say using KVL in the loop 1, I will say that it is equals to E of t applied voltage is equals to VR1 plus VL1 plus VC. This is equation number 1. Loop 1. Similarly, at loop 2, I can write that VC is equals to VL3. This is L2. VL2 and VR2. This is my equation 2. This is my loop 2. Okay, I can write a node equation here. I will say using KCL at this point and node x3, I can write that I have a current entering I1 which is leaving two different paths. With I2, second is basically IC. This is my third equation. Here we have three energy storing elements, that is L1, L2 and capacitor. Inductor stores energy by virtue of current, so we have I1 state variable, second state will be I2 and the third state variable is the capacitor voltage which is VC. So let's define the state variable. Here we have three state variables. First state variable is basically x1, second state variable is x2, third state variable is x3. x1 is equals to say I1 which is inductor 1 current, this is I2 which is inductor 2 current, and we have VC. These are the two inductors current, and this is basically our third capacitor voltage, because inductor stores energy by virtue of current and capacitor stores energy by virtue of voltage. So these are the all three state variables. So using equation 1, 2 and 3, we can write all these x1 dash, x2 dash and x3 dash state equations. x1 dash will be d I1. Okay, using equation number 3. So using equation number 1, which is equals to u is r into e of t is equals to vr1 plus vl1 plus vc. So this is basically my state value variable u. Vr1 can be written as I1 into R1 plus L is equals to LD I1 plus VC. So this is U. I1 is basically X1, R1, L1, DI1 is X1 dash, VC is X2. So my equation becomes, my first state equation x1 dash is now evaluated by rearranging this term. This will become minus r1 over l1 x1 minus 1 over l1 x2 plus u over l1. This is my first state equation. I will name it as equation A. For second equation, I will use second equation using equation number 2, which was BC is equals to VL2 plus VR2. Here we have VL2, this will be equals to LDI by LDI L2 inductor, second inductor current, and this, from this equation we can find the x2 dash. So VC is basically a parameter x3, which is L2 DI2. DI2 can be written as x2 dash plus VR can be written as R2 into I2. I2 is basically x2. So I can evaluate this x2 dash by rearranging this equation. This will become x2 dash is equals to minus R2 over L2 x2, similarly minus x3 over L2. This is my second state equation. This is equation B. Now I want to find a VC dash or DVC. We have a third equation which contains capacitor current. Capacitor current is basically it can be transformed with the help of capacitor mathematical representation, that is IC equals to C DVC. In that we have DVC involved, so we can find the x3 dash. So I can write here using equation number 3. What I can say, I1 is equals to I2 plus IC. This IC is equals to CDVC. This is basically the mathematical model of capacitor. So I1 is basically my x1, I2 is x2, and this is CDVC is basically x3. This DVC is VC is x3, DVC will be x3 dash. So I can evaluate this x3 dash from rearranging this equation, and this will become 1 over C x1 minus x2 over C. This is my third equation, state equation here. So now I can write the complete state space model of this system. This will be equals to x1 dash, x2 dash, and x3 dash x1 dash is equals to minus r by l1 r1 by l1 x1 1 over l1 x2. No dependency on x3, so it will be minus r1 over l1. Similarly, second one is minus 1 over l1 x2. This is VC, this is basically x3. This is x3, this will be x3. So this x1 depends on x1, no dependency on x2, and this will be equals to minus 1 over l1 x3. This is x1, x2, x3 plus here the equation A depends on u as well. The coefficient is 1 over l1. So I will write it 1 over l1. x2 dash depends on minus r2 l2 and x3 over l2, no dependency on x1. So I will write no dependency on x1. This is minus r2 over l2 or minus 1 over l2. No dependency on u as well. Okay. This is plus here. This is x2 dash, this x3 was present here, and this is plus x3 over l2. So this is 1 over l2. And x3 dash is equals to 1 over c x1, and x2 is equals to minus 1 over c, no dependency on x3, no dependency on u. So this is the state space representation here, and finally we have an output equation y, which is equals to, here output of this system was given in mentioned in this question, which is basically I2 is our state variable x2, so I will write 0 1 0 x1 x2 x3 as x2 is I2 is my output. So this is output equation here, and this is the state space representation of this electrical system. I hope that this thing is clear to you, and this system can be represented with the help of that state space representation. Output is the current through this resistor. So first of all, we need to write the equations here using KVL. In this loop, I can write that V of T input is equals to VL plus VC. Here we know this these two resistors, this resistor and the capacitor, these two elements are in parallel, and in parallel we have similar voltage here. R resistor and capacitor are in parallel, so VR is equals to VC. So this voltage is equals to the VL plus VC. I will say this is my equation number 1. Second equation will be the current at this node. So I have an entering current IL. IL is equals to IR plus IC. This is my equation number 2. I have two energy storing element. One is inductor current, second is the capacitor voltage. What I can do, that I can select state variable here. The state variables are x1 is equals to the inductor current IL. Similarly, x2 is basically capacitor voltages here. So these are the two static variables, and third variable will be the input, which is basically V of t. I have equation number 2. I can write equation using equation 2. Using equation number 2, I can write it IL. This is the state parameter. Similarly, IR is no more our state variable, so I would like to write this variable in the system parameter as a state variable. So I can write it as VR over R. IR is equals to VR over R, and VR can be replaced as VC over R, and VC is equals to VR here, because these two elements are in parallel. So I can write this term as VC over R. This is my state variable. Second is IC can be written as CD VC. This VC dVC is basically x2 dash, so I can evaluate x2 dash here. This will be IL is my x1, VC is my x2 by R plus CX2 dash. So x2 dash will be equals to x1 over C minus x2 over RC. This is my first state equation x2 dash, which is written as A, which I named as A. Second equation can be evaluated with the help of equation number 1, which is VT. You can write using equation number 1 here. This is VT, which is this equation is basically input voltage is equals to capacitor voltage plus inductor voltage. So the applied voltage V of t is my state variable U. VC is basically state variable x2, and VL can be written as LDIL. This DIL is basically x1 dash I1. IL is x1, DIL will be x1 dash. So x1 dash can be written as U by L minus x2 by L. This is my equation B of second state equation. So I can write my state space representation. This is x1 dash, this is my x2 dash, is equals to x1 dash is equals to no dependency on x1 here, so b0, and this is minus 1 over L. For x2 dash, this term is basically 1 over C and minus 1 over RC. You can have a look at here, etc. This is 1 over C minus 1 over RC. So this is x, this is x1, x2 plus x1 dash depends on u as well, so the coefficient is 1 over L and there is no dependency on u, so this is my state variable or state space representation. Here the output equation, the output value is IR, which is equals to V C over R, that is x1 over this is VC is basically x2 over R. So I can write my output IR is depends on x2, not on x1, not on inductor current x2, and this is 1 over R. Basically this is IL, this is capacitor voltage, this is basically this equation. IR is equals to VC over R. So this is the state space representation of our system here. I hope that this question is clear.